Okay, so this is where we stopped last time, right? We had discussed about biosynthesis of isoleucine. I know that you are still left to write this part down, if I'm not wrong. But let us quickly go through the pathway once again because we had finished it at the last moment. So just quickly, let's go through it and then I will give you time to note it down. Okay. We said that the precursor for biosynthesis of isoleucine is going to be threonine. So you can very well see over here that threonine is COOH, CH, NH2, CHOH, CH3. So the first reaction that you carry out is deamination reaction, wherein you remove ammonia, which is NH2, and the hydrogen, which is adjacent to it. This both is going to be released in the form of ammonia. Now, when you do this, the oxygen of the adjacent carbon is going to be moved up. It's going to be moved up from where we are removing the ammonia. So you get CH3, CH2, CO, COOH, which is alpha oxobutyrate. Now, here we condense alpha oxobutyrate with pyruvic acid. But when we do this, we remove the carbon dioxide from pyruvate. So the COO group is removed. What will be transferred to alpha oxobutyrate is CH3CO and this hydrogen. Okay, so the CH3CO goes at this point. It's going to be attached over here. So it becomes CH3CO, and you move this CH3CH2 that you see over here on the top of this carbon. So that's how you get CCH2CH3, and the oxygen there gets this hydrogen which is coming from pyruvate, so that it becomes hydroxyl group. So that's how you get alpha aceto alpha hydroxy butyrate, post which you carry out a reduction reaction. And during this reduction reaction, you will basically see that you are shifting the CH2 CH3 group that you see over here to the adjacent carbon. And hence, this carbon that you see over here will get a hydrogen, which is coming from NADPH. And this oxygen also that you see over here will get another hydrogen, which comes from NADPH and H plus. So that's how you get two hydroxyl groups. So it becomes alpha beta dihydroxy beta methyl valerate. Now you carry out dehydration reaction. So the dehydration reaction is carried wherein one hydroxyl group is removed and one hydrogen from the hydroxyl group is removed. So that's how H2O is going to be removed. We move this CH2 down, so it becomes CH3, CH2, CH, CH3. So the hydrogen is moved to the adjacent carbon over here, as you can see. Okay. And this becomes CO because this oxygen is as it is, and COOH. So alpha oxo beta methyl valerate is what you get. Now, to make it an amino acid, you need an amino group. So that amino group is going to be donated by glutamic acid, which donates the amino group and gets converted to alpha Kg. So here is where you will add your amino group. So you have to get rid of this oxygen, which goes with alpha Kg. So you get CH3, CH2, CH, CH3, CH, NH2, because obviously it comes in the form of NH3 from glutamate. So NH2 and hydrogen will be added over here, COOH. That is your L-isoleucine. And this is basically brought about by a transaminase because you are transferring the amino group from glutamic acid to alpha oxo beta methyl valerate. Okay, that's how you synthesize uh, isoleucine. So I will go to the top of this pathway. You can give the heading as biosynthesis of isoleucine, and you can start writing. Gradually, I will scroll it down. Okay, see to it that you are noting all the enzyme names correctly. Okay, you can start writing. Just give me a minute. Okay, are you all? Have you completed writing this part?
Yes, sir.
Yes. Okay, great. So let us go back to that first pathway that we did, wherein we saw what are the different aspartate family amino acids that we are going to synthesize. There we saw synthesis of three amino acids, if you remember. We saw how aspartic acid is synthesized from oxaloacetate, how asparagine is synthesized from aspartate, and also how you basically synthesize threonine out of aspartate. Post which we discussed how homoserine can be converted into methionine, if you remember. We also saw how threonine is converted into isoleucine, which we just revised. And now what we are left with is to see how aspartate semialdehyde is converted into lysine. So that's the sixth and the final amino acid of the aspartate family whose biosynthesis we are going to discuss. Now, this biosynthesis may look slightly complicated, though it is not really very complicated. It may just fear you by the structures that it involves. But still, I would say that if you practice it enough, there wouldn't be much of an issue. So, let us start with understanding how biosynthesis of L-lysine is carried out. We already know that the precursor that's involved in this particular scenario is aspartate semialdehyde. So let us better start with aspartate semialdehyde over here. You very well know that in exam, if they ask you, you have to see from which raw material they have spoken about the synthesis of lysine. So accordingly, you will have to start. So if they say that show the biosynthesis of L-lysine from oxaloacetate, then you will have to show from oxaloacetate how aspartate semialdehyde is formed and then continue from aspartate semialdehyde to the rest of the pathway. I hope that makes sense to all of you. So now without wasting any further time, let us delve into this pathway. So aspartate semialdehyde is something like this. This is your aspartate semialdehyde. Now, let me tell you that in this, what you are basically going to carry out is a condensation process. You are going to add pyruvate to this. Okay, you're going to add pyruvate to this, and two water molecules in this condensation process is going to be released out. When you add pyruvate to this structure of aspartate semialdehyde, you will see that you get a close ring structure which is involved. Obviously, now you will have two carboxyl groups because pyruvate also has a carboxyl group, right? So this structure that you see right now is called 2,3 dihydropicolinate. And obviously, because you are carrying out condensation and you are fusing two compounds to form dihydropicolinate, the enzyme that's going to be involved over here is dihydropicolinate synthase. So you're fusing pyruvate and aspartate semialdehyde, removing two water molecules in the process, and you are synthesizing dihydropicolinate. Enzyme is dihydropicolinate synthase. The next step that you will do to this is you will carry out reduction, and it's very obvious that when you carry out reduction in this and you're adding hydrogens, you are going to absolve one of the double bonds that's involved over here, correct? Now, the donor of hydrogens is going to be NADPH. In most of the anabolic processes, biosynthetic reactions, whenever you have to carry out reduction, you will see that the donor of hydrogens is NADPH. So you will add the hydrogens to the structure, and what you get is going to look something like this. This double bond is as it is. The double bond that we have absorbed is this one. Okay, we have removed that by carrying out reduction. We have converted it into a single bond. This structure that you see is what you call as tetrahydro dipicolinate. Okay, tetrahydro dipicolinate. Now, because you have carried out reduction over here, the enzyme that is going to be involved is called dihydro. Okay, this should have been, just a minute, I need this error. This should have been dihydro dipicolinate because you have two carboxyl groups. So either be it should be dihydro dipicolinate synthase. Sorry. So dihydro dipicolinate reductase will be your enzyme, which is responsible for reducing dihydro-dipicolinate into tetrahydro-dipicolinate. Dipicolinate, this word comes because you have two carboxyl groups involved. Okay. Now, the next step is going to be to break open this ring-shaped structure, because any which ways we know that lysine is not a ring-shaped structure. Okay. So we are going to break this ring-shaped structure. How are we going to do that? So again, there is going to be a condensation that we do to break this structure, wherein now what we are condensing to tetrahydrodipicolinate is succinyl CoA, and in this process, what you get out of the system is coenzyme A. Okay, so the succinyl group is going to be incorporated into your tetrahydrodipicolinate structure. Now let us see what do you get when you do this. So you get COOH, CO, CH2 thrice, CH, COOH, NH, CO, CH2, CH2, COOH. So this section that you see over here is the succinyl group, which has been combined to this part. Okay. Now this structure will be called N succinyl, because the succinyl group is as it is, N succinyl 2 amino 6 oxo pymylate, because the amino group is on the second carbon. Okay, there is an ketonic group over here, so 6 oxo pymylate. Okay. Now, because you added succinyl CoA to break the ring shaped structure, the enzyme has a slightly different name over here. Okay. So the enzyme is going to be tetrahydrodipicolinate succinylase, because you're breaking the ring shaped structure to form an open structure. using a succinyl CoA group over here. So you call it as tetrahydrodipicolinate succinylase. Let us repeat till this part what we have done. We started with aspartate semialdehyde. To aspartate semialdehyde, we added pyruvic acid. We carried out condensation, two water molecules were removed. We formed dihydrodipicolinate. The enzyme was dihydrodipicolinate synthase. To this, we carried out reduction. NADPH and H plus were the donors of hydrogen getting converted to NADP. We resolved one of the double bonds, we converted it to a single bond, and we formed tetrahydrodipicolinate. Dihydrodipicolinate reductase was the enzyme which worked here. Then to break the closed string structure into an open structure, we condensed succinyl CoA over here. CoA was removed. You formed N-succinyl 2-amino 6-oxopymalate. Because succinyl CoA was used to break open the structure, we have the enzyme tetrahydrodipicolinate succinylase, which works in this place. Now let us see what happens next. So in the very next step, please understand that lysine, I hope you all know that lysine is a diamino acid, which means it has two amino groups involved. Okay. So that is the basic reason why you will see that currently in the structure we have only one amino group. So we need one more over here. So where is that one more going to come from? So that one more is going to be donated by glutamic acid. Again, we are talking about an aminotransferase reaction, being carried out over here. And what you get is obviously your alpha Kg or alpha oxoglutarate, as you call it. Okay. So where is this amino group going to be added? It's going to be added to this carbon. So that oxygen will be removed. Okay. And that oxygen will go as a part of alpha Kg. So what you will get is COOH, CH, NH2. Because remember, glutamate gives it as NH3. So oxygen is removed, कार्बन को एक हाइड्रोजन मिलेगा और एक NH2 ग्रुप अटैच होगा. इसके नीचे CH2 थ्राइस था ही, CH, COOH, NH, CO, CH2, CH2, COOH. So this compound that you see is now still N-succinyl because the succinyl group is as it is. 2,6 because on the second carbon and on the sixth carbon, I have amino groups now. So I will call it as 2,6 diamino pymalate. That's my compound. Okay. Now, what's the enzyme name? The enzyme name is unfortunately going to be quite long over here because glutamate is the donor. We have glutamate, succinyl diamino pymalate aminotransferase. So this indicates that you are transferring the amino group from glutamate to form succinyl diamino pymalate. So that's the enzyme name, the long enzyme name that you have. It's a highly specific enzyme. It's a specific aminotransferase which will work only for this reaction and will not carry out aminotransferase catalyzed reaction for any other substrate. Now we are very close to getting our product, though there are few reactions to go, but we are quite close. So let us see what happens next. The next step that you will see is you add a water molecule and you remove succinate or succinic acid. So now you should realize why water, because if succinate has to be removed, this has to get a OH group such that COOH, CH2, CH2, COOH is succinate. That's how that will be removed. So एक OH चला गया उसमें और एक जो हाइड्रोजन होगा that is going to be added over here to make it NH2, right? So what am I going to have? I'm going to have COOH. I will have CHNH2. I will have CH2 thrice, which is as it is. Then CHNH2 COOH, and succinate is removed. So what you see right now is called L comma L alpha epsilon diamino pymolate. अल्फा एप्सिलॉन नहीं लिखना है तो 2 और 6 भी लिख सकते हो, कोई प्रॉब्लम नहीं है. 2,6 diamino pymolate लिखोगे तो भी चलेगा. It's going to be one and the same. Okay. Now the enzyme which is working over here, we call it as succinyl diaminopymolate desuccinylase. बिकॉज अगर तुमको याद हो तो जब हमने सक्सिनल ग्रुप ऐड किया था, that was to break this ring shaped structure and we called it as succinylase. Now as you are removing that succinyl group, the enzyme that works over here is called as desuccinylase. So getting rid of that succinyl group and you're releasing it in the form of succinic acid. Okay. Now the next reaction is a very chiller chindi reaction because it's just involving adjustments. It's an epimerase reaction wherein what you are going to do is that this NH2 group, you're going to shift its orientation to the other side. Okay, that's it that you're going to carry out. So you will have COOH, CH, NH2, CH2 thrice, CH, NH2, COOH. So you have just changed the orientation of the amino group from one side to the other side. And the product that you get is called meso alpha epsilon. If you don't want to write alpha epsilon, you can write 2,6 diamino pymolate. The enzyme that works over here in this scenario is called diamino pymolate epimerase. That's the name of the enzyme because you're converting it into an epimer. Okay, so just changing the orientation of NH2 group there on the second carbon. And what's the final step? The final step is release of carbon dioxide. We are going to release CO2. Okay, so we are going to release CO2 from here, and this hydrogen will move up. Okay, so it's pretty obvious that what I'll have is COOH. I will have CH, NH2, CH2 thrice, CH2, NH2. करेक्ट. ये CHNH2 हुआ करता था ऊपर, अभी वो कार्बोक्सिल ग्रुप का हाइड्रोजन ऊपर चला गया है, CH2 NH2. दिस इज नथिंग बट lysine. So you have just carried out decarboxylation, and the enzyme that works over here will be called diaminopymolate decarboxylase because you removed carbon dioxide from diaminopymolate. So though quite a lengthy process, it's very much understandable if you practice it. It's not very difficult. Okay. So have you all understood the reactions? At least I don't expect you to know all the reactions right away, but have you understood what's happening in the process, everyone?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. So get to writing down the reactions. Okay, are you all done writing?
Yes, sir.
Okay, others?
Yes, sir.
Okay, so there's a small change that I had to announce for today. Your practicals will begin at 12 today instead of 11 because Varsha ma'am has a meeting to attend. But you're not free. Don't get so happy. You will join the lecture link at 11:10. Mind you, I said lecture link, not practical link. You are going to join the lecture link at 11:10. So 11:10 to 12, I will engage a lecture, and 12 o'clock we will switch to pracs. Okay, that means that we'll go to the practical link. Okay, fine.
Yes, sir.
Okay, so that is it for now. See you at 11:10. Thank you.